Welcome to this video on reaction mechanisms. Reaction mechanisms are one more way of figuring out a rate law from a reaction. And what they do, what a reaction mechanism does for us, is it shows us the route of a reaction, right? A route or a pathway from reactants to products. So here's an example of a chemical reaction, right? I can take two gaseous nitrogen monoxide molecules and I can react them with two H2 gas molecules to make an N2 gas and two waters. And the thing about this reaction is that this particular thing here is what we call an overall reaction. Shows all the products making all of the reactants. But we've already seen with collision theory that reactions happen, right? A reaction happens when particles collide. And the thing about the collisions is they have to have the correct energy. We'll get there later. That's not super important to what I'm talking about here. The correct energy and the correct orientation. So that reaction, the way it's written, actually requires two NOs and two H2s to collide with each other in such a way, in such an orientation, as to spit out an N2 and two waters. And one way that I think of reactions is that in order to get a reaction to happen, herding molecules is like herding cats. In other words, you're not going to get very much cooperation out of them. To get four molecules to do exactly what you want to make those three things is pretty near impossible. And so this does not happen in a single step, right? This is an overall reaction, but it's not one step. There's a route that this reaction takes. There's a pathway. It turns out that the pathway for this reaction has three steps. And so what happens is first, two NO molecules, just two NO molecules collide. And what they do is they make one molecule. They make N2O2. So we make two molecules out of one. In a second step, that N2O2 molecule collides with an H2 molecule, and we get an N2O and a water. And then in a third step, the N2O that got made in step 2 reacts with the other H2 to make N2 and H2O. The end result is exactly the same, right? The overall for this reaction, if I look at it, there's N2O2s canceling each other out. There's N2Os canceling each other out. There's H2s adding to each other, and there's waters adding to each other. I'm left with two NOs, two H2s, making an N2 and an H2O. So it checks out. The overall reaction is exactly the same, even through these three steps. The other thing I want you to notice is that the reaction mechanism indicates slow versus fast, which is something that we'll get to later. For now, I just want to point out a couple of things. Each of these steps is what we call an elementary step. So step 1 is the first elementary step. Step 2 is the second elementary step. The third step is step 3. And the way that we classify our elementary steps is by their molecularity. And all that molecularity is the number of particles involved in that step. So if I look at step 1, there are two particles, right? There's an NO and there's two of them. So I call this bimolecular. Why? Because there's two molecules involved. In step 2, I see two molecules. So step 2 is also bimolecular. And in step 3, you guessed it, here's one and here's the other one. This is a bimolecular step. Bimolecular is pretty common because it's not too hard to get two molecules to collide with the right energy and the right orientation. Every once in a while, you'll get what's called a unimolecular step. Not in this reaction, but somewhere else, right? That's one molecule involved. every once in a great while, you'll get what's called a molecular step, right? 3 particles, 3 molecules involved. And all that this is it's just counting up the number of molecules that are reactants in a step, right? If there's 2 molecules involved in a step, it's bimolecular. If there's 3 molecules involved in a step, and this is reactants, it's termolecular. So molecularity is helpful to us. Another thing that we're going to want to do is we're going to want to classify our different substances in this step. We know what reactants and products look like, right? That they go in on the front side of the intermolecular of the overall reaction, right? Reactants are at the front of the arrow in overall steps. Products are in the back, so they go after the arrow. But now there's these new classes of things as well. So let's take a look at that. The 2 other classes that I'd like to look at, aside from products and reactants, that we see in a reaction mechanism are the class of intermediates, reaction intermediates, and catalysts. So intermediates appear as a product, and then they later disappear, right? On the other hand, catalysts used as a reactant later reappear as a product, right? So neither of these, right, they don't appear in the overall. You'll never see an intermediate or a catalyst in an overall reaction. The difference comes in which ones they are. So intermediates show up and go away again. Catalysts go in and come out again. Catalysts are not consumed, right? That's another way to think about catalysts. Whereas intermediates are produced and then consumed. So I can tell in my reaction above that I have 2 intermediates. Do you see how N2O2 shows up in step 1 and then it disappears again in step 2? So N2O2 is one of my intermediates. There's actually a second intermediate, and you may have spotted it already. N2O appears in step 2, and then it disappears again in step 3. Intermediates are generally the hardest things to pin down in chemical reactions because they usually don't stick around very long. In fact, it's pretty rare in a reaction to be able to isolate an intermediate. And so the big part of experimental studies for reaction mechanisms is trying to find them or find evidence for them. And when you can, that helps you nail down a reaction mechanism because you, again, cannot find mechanisms without doing experiments. There are no catalysts in the reaction above, right? You don't see anything going in on the reactant side and coming back out again at the end. We'll find catalysts in some other examples in class. So the last thing we'd like to do is to try and learn how to write a rate law from a mechanism. So let's look at this reaction one more time. So looking at this reaction one more time, I'd like to call your attention to the speeds of the steps. You notice that there's slow, fast, and fast. And that's the way that we'd always look at a reaction mechanism. One step will always be the slowest. They could all be really, really fast, but the slow step is the slowest of them all. And so what I want you to know is that rate laws come from the slow step of a mechanism. So we start by writing the rate law from the slow step. And by the way, when I have a mechanism, if I have an elementary step, and by the way, only an elementary step, I can't do this for any other type of thing, but if it's the step in a mechanism, the coefficient equals the exponent, right? I told you in an earlier video that we can't do that. We have to figure them out from experiment. Well, we did the experiments to get the mechanism. And when I know the elementary steps of a mechanism, I can use the coefficients as the exponents. And so for this rate law, I start with the slow step, which appears to be step 1. And I use the reactants. I notice that the reactants are NO. And so I would say that rate equals K times NO. And again, because this is an elementary step, I get to turn that coefficient of 2 into an exponent of 2. So apparently, according to this mechanism, I would expect that the rate law is second order with respect to nitrogen monoxide. Now I always have to check, right? What am I checking for? Are there any intermediates in the rate law that I just wrote? Okay. I look at this and I say, did any of these things in the slow step, were any of them intermediates? If the answer to that is no, we are happy because we are done. If the answer to that is yes, well, I've got a little bit more work to do. In this case, I look at NO and I remember that my overall reaction was 2 NOs plus 2 H2s makes N2 plus 2 H2Os. And so my check is that NO equals a reactant. Reactants, catalysts, and even products can show up in a rate law. The only thing that can't show up is intermediates. When there are intermediates, we do more work. So that's how we get from mechanisms to rate laws. We'll do some more complicated examples in class soon.